Now we're in chapter 1.3, and we're going to be looking at behavior of graphs of functions and kind of tying it to some things that we did before. So remember the definition of a function. Let's just write this down again. Um, every element in the domain is matched to exactly one element in the range. What does this definition look like graphically? So we know about looking at a table, looking at a graph of ordered pairs, whether something's a function or not. Basically, we're saying every x value cannot have more than one y value. So if I just give myself just give yourself a graph of like whatever function, it means that every x value, no matter where it is, only corresponds to one point on the graph. And so we have something called the vertical line test, which says if a vertical line passes through, I'm just going to say f of x, a function, more than once at any let's say x value, any input, then f of x is not a function. So this function that I sketched here, I can draw a vertical line anywhere through the function, and we would say this passes the vertical line test. Now it's important to note on your AP test, AP exam, if you have to explain why something is a function or not a function, you can't just say vertical line test. So not and not sorry. I want to say not a justification, not a good justification. Instead, they want you to say the vertical line test is just a visual representation of the definition of a function. Because if a vertical line passes through a function in more than one place, it means that that x value that the vertical line represents, vertical line is like x equals c, right? It means that that vertical line has more than one output assigned to it. So that x value has more than one output assigned to it. So you can't use vertical line test to say why something is a function. You must write out definition of a function. So what I put in red at the top of the page. With that said, in my brain, I'm always using vertical line tests anytime I think of a graph. Use a graphing utility to view the graph of the equation. I've got to fire mine up here. Then determine whether the equation represents y as a function of x. Part of the reason I wanted to do this was just to make sure that you know how to correctly type things into your graphing calculator. We have you guys buy these things for high school, and then sometimes you don't end up needing to use all of the features in some of your earlier classes. So it's easy to, I take for granted sometimes that some of this maybe you've never really done or you've only done once or twice. So if this is old hat for you, then that's good. First of all, let's go to y equals. We've been working with scatter plots, but the graphs are not going to work if we're trying to plot stuff too. So go up to plot 1 and press enter to unhighlight it. Clear out any old equations you might have. Okay, and so if I want to graph this first equation, it is ready to graph if it's in y equals mode for our graphing calculators. So we can just type in 1 divided by 2 for 1/2, or you could say 0.5. X is this key next to alpha. The t, the theta, the n, those are the variables you get if you change the mode of your calculator, which we are not going to do. X squared minus 2x plus 3. Hey, common mistake, I want to point this out. Sometimes we accidentally type in negative instead of minus. Notice the difference on my screen. It's smaller if you type in the negative. So if you ever get a graph and you're like, gosh, I typed in the same thing, why does mine look so weird? That's a really easy thing to do, so be careful, because that means times negative 2x. Anyway, and then because our windows have been zoomed for stats stuff, let's zoom 6 back to standard. All right, this is a quadratic. Hopefully I would know that without having to graph it, but again, just to practice graphing. So I'm thinking about the vertical line test. This parabola would pass a vertical line test. Anywhere I draw a vertical line, it would just be giving one y value for every x value. So I'm just going to write function. What if the equation is not solved for y? So our equations, when we press y equals, they're not set up to be y squared equals, or we're not allowed to have x and y on the same side. So you need to solve this for y. Subtract x squared. Because we're going to be square rooting both sides, we need the plus or minus. And so when you write this in, you need 2 lines on your calculator. One can be the positive square root of 16 minus x squared. And then to get the full graph, you also need the negative, use the negative, not the minus, square root of 16 minus x squared. And then we don't need to zoom 6 again, but we can zoom 6 for standard. We could also just hit graph. Now this looks oval because my screen is not, you can see the y-axis. When it goes negative 10 to 10, it's shorter, more smushed in there than the x-axis. You could also do like zoom square to make it look a bit better. This is a circle, right? We should recognize this equation as a circle with a radius of 4. Okay, but if I just do my zoom standard, it looks kind of elliptical. There are points at negative 4 and 4. It's just hard for the calculator to show that detail. Is this a function or not? No, because those two pieces, even though they look like two different graphs, remember that is the complete graph. It would be the same color. That fails the vertical line test everywhere except for a negative 4. So not a function. But if I had to justify, I wouldn't just say because it fails the vertical line test. I would say because there are multiple inputs that have a plus or minus y output. Okay, and then go back to y equals, clear those two equations out. The last one was 1 divided by the square root of 25 minus x squared. This one looks kind of weird, right? But does it pass the vertical line test? That answer is yes, because it is kind of hard to see. But if you trace along, if you press trace, you can kind of move along. You could zoom in if you want to. This is a smooth curve. It's not like somehow overlapping itself. So yeah, we are only getting one y value for every x value. And we should know about domain, right? We can't get anything past negative 5 or 5 because then you'd be square rooting a negative. So yes, this is a function. Looks weird, but it is one. Increasing, decreasing, and constant functions. So a function is increasing on an interval when for any x1 and x2 in the interval, let's do a sketch here. Give yourself an increasing function, give yourself an x1 and an x2. This would be f of x1. Excuse me, this would be f of x2. Okay, so a function is increasing when for any x1 and x2, if x1 is less than x2, which is how I have this picture drawn, that implies that f of x1 will be less than f of x2. So that's kind of a technical way of just saying, like, yeah, if a function's increasing, the point on the left, the point you hit first, is going to be lower than the point on the right because the function's increasing. And so similarly, think about something decreasing. Same idea, give yourself a decreasing function. I'm not going to write my function notation this time. If x1 is less than x2, so the first point compared to the second point, f of x1 should be higher than, greater than f of x2, if you have a decreasing function. I'm going to be honest, another reason I'm drawing these out is so that it's hard for me to just think about this abstractly without drawing the picture. So you're welcome to draw anytime you're trying to think of this. A constant function is just a function that is a horizontal line like that. So let's say this is x1, over here is x2. x1 could be less than x2, but f of x1 is equal to f of x2. It doesn't matter which point you look at first, they're both the same height. All right. Determine the intervals on which f of x is increasing, decreasing, or constant. We're told to use intervals. When we use intervals, the rules here are that we only use x values. In other words, we're kind of giving mini domains. Always use open intervals. What does that mean? Parentheses only. Because if you think about it, let's look at one of these graphs. Let's look at this graph in the middle here. This point where the graph changes from increasing to decreasing, that maximum point there does not fit our definition of increasing or decreasing, right? Because if I compare this point to this point, then those two, the function is increasing right there. But if I look at this point compared to here, it's also decreasing. So, what is the value? Those changeover points are not considered to be increasing or decreasing. All right, so figure A. We have to trace this from left to right. So looking here, we are always going up. This function is increasing from negative infinity to infinity. It's not constant right here. It kind of looks constant, but it's just we're not zoomed in very far. But the graph hits 0, 0. Immediately to the left, think of x cubed. Plug in negative 1/2, you get negative 1/8. Plug in 1/2, you get positive 1/8. So anything close to 0 on either side will not be exactly 0. So will not be constant. Okay, there's no constant section, there's no decreasing section. So if you're doing homework tonight, I might have something like this on my answer key. This function is increasing as we follow it from the left, and then it decreases, and then it increases again. So when we list out our increasing, we're going to say, start on the left, negative infinity, excuse me, negative infinity until, remember, use the x value, negative 1. So if I say go to that domain, you should see a function that's increasing. Also, it's increasing from the domain positive 1 to infinity. The graph is decreasing between negative 1 and 1, and there is no constant section. And then this little piecewise graph here, we can see it's got a positive slope, then a 0 slope, and then a negative slope, confirmed here in our equation. So the graph is increasing on the left from negative infinity until the x value 0. The graph is constant from 0 to the x value 2. And the domain for decreasing is 2 to infinity. Relative and absolute extrema. A function has a relative maximum at any point where the function changes. So again, I'm going to sketch this out. Relative max is like this. So where the function changes from increasing to decreasing. A function has a relative minimum any point where the function changes from decreasing to increasing. A function that changes from constant to either increasing or decreasing is said to have no relative extrema. So here's a function changing from constant to increasing. The reason we say this is not a relative min is because it is no lower than the points directly to the left of it. So sure, it's a relative, it's a minimum spot compared to the right side of the graph, but not really to the left side of that point. Or like same thing here, to go from here down. That's not a relative max. And absolute minimum or maximum value can occur on any closed interval. So again, a closed interval is one that means we're looking at endpoints. So we're not going out to infinity. We're maybe saying like, okay, here's a graph. Maybe this graph goes on forever, but I'm asking you to look at the closed interval between 1 and 10. I'm just looking for this segment. Is there an absolute lowest and an absolute highest point on this graph? Yes. Lowest is somewhere here. Let's pretend that this point is higher. I didn't draw it very well. But if I expand it to the whole thing, is there an actual ceiling highest point on the entire graph when it has these arrows off to the end? No, this goes on forever. No actual minimum point. This goes on forever. But if I close the interval and say, just look here, negative or positive 1 to 10, there we have an absolute max and an absolute min. These absolute min and max values can occur either at endpoints of the interval or relative extrema. Extrema, extreme points. Extremum is a singular point. Extrema just means max or min. Relative max, relative min. So same thing with absolute. Absolute min or max, absolute extrema. This is something, relative extrema, absolute extrema, this is something that we look at not only in AP Pre-Calc, but also AP Calculus. You'll be using some calculus to kind of prove why something has to be a max or a min. So this is just sort of our intro this year. So on the graph below, label the relative and absolute extrema on the interval -2 to 4. So first of all, let's look at -2 to 4. So here-ish to just kind of like estimate where that is. Here to here, we're just looking at this interval. Ignore the other stuff. We're not going to ask, I'm not asking you to label the actual ordered pairs. I'm just asking you to say, there's a relative min. Wow, really? There's a relative max. There's a relative min. Here's a relative max. And this is the end of the interval, right? Here's a relative min. Almost missed one. What about the absolute? The absolutes are the ones that are the actual highest and lowest points. In this particular picture, it's the end points in both cases. This is the absolute max, the highest point on that entire graph. This is the absolute min. If this graph had some sort of like big fluctuation here, then that would have been the absolute max. Okay, so it's not always the endpoints for the extrema, but it can be. I don't consider the relative max or min to be these endpoints here. Different textbooks disagree. Even our definition for our AP Pre-Calc is a little bit iffy the way they've introduced it to us this summer. So I'm going to stick with what we go with in calculus. So relative extrema cannot be endpoints, but absolute extrema can be. Average rate of change is huge on our AP test. It's all over the place. You are going to be asked in free response to calculate an average rate of change, and hopefully you will just say, that's super easy. I'm just finding the slope between these 2 points. So recall the difference quotient. We talked about this a couple days ago. The slope of a secant line that passes through any 2 points on f of x is f of x plus h minus f of x all over h. And remember, this represents the slope between any 2 points, h units apart, on f of x. Average rate of change is just the difference quotient. It's just the slope between any 2 points on some interval a to b. Okay, so average rate of change right here, average rate of change for this function, it's written right here, but I want to write it out. It's f of b minus f of a over b minus a. You could subtract it in the other order, but in some cases you'll get a negative over a negative to get a positive. It's just considered more simple to do the second point minus the first point. Okay, so average rate of change formula, exact same thing as the difference quotient. It's just that the notation, how we're doing things, how we're looking at things, is different. A and B are usually constants, and average rate of change is usually a number that we're going to get and interpret. Find the average rate of change of each function on the specified interval. So find the average rate of change on this graph, meaning if we were to graph this thing, I don't know what the graph really looks like, something like that, from -2 to 2, we're trying to figure out what's the slope. That just means that we should be doing f of 2 minus f of -2 over 2 minus -2. It is a good idea to show this work because if this is part of a free response for AP Pre-Calc, they will possibly give you a point or want this to be part of your work to earn your point. All right, what do we get when we plug in 2? We get 2 times 8 minus 2 times 2, so minus 4 plus 1, minus, use parentheses here. What do we get when we plug in -2? We get 2 times -8 plus 4 plus 1. All of it's over 2 plus 2 is 4. We get 16 minus 4 plus 1. Let's just come up with that math, right? 16 minus 4 is 12. 12 plus 1 is 13. And then in here we get -16 plus 4 is -12 plus 1 is -11 minus -11. 4. So the average rate of change is 24 over 4, so 6. If we were to actually graph this, my picture's a bit off, obviously. If we were to actually graph this, the slope between the 2 points that close off this interval is a slope of 6. In part A, we were given an equation. In part B, we're given the information via table. So the inputs are x, the outputs are f of x. We want the interval from -4 to 7. So f of 7 minus f of -4 over 7 minus -4. F of 7 is 10 minus f of -4 is 12. 7 plus 4 is 11. I get -2/11. That's our average rate of change. Okay, if a function is nonlinear and continuous, no holes, asymptotes, gaps, and the average rate of change is positive on the interval a to b, which of the following must be true? You can give yourself some kind of sketches. Average rate of change. So here's A, here's B. We've got a positive average rate of change. So the point at A has to be lower than the point at B. I don't want to draw it in yet. Let's just see. F of x must be strictly increasing, meaning can't dip around and decrease. But what if f of x does look like this? Is that still an average rate of change that's positive? Yes, and that's a continuous graph and it's nonlinear. So 1 does not have to be true. Is f of a, the output, the function value, bigger than f of b? No, that can't be true. And again, this interval notation implies that a is less than b. F of a does have to be less than f of b to get a positive rate of change, so that seems right. F of x has an absolute maximum on the interval a to b. That doesn't have to be true. Oh, no, wait. Yes, that does have to be true. I was reading that as does the end have to be the absolute max. F of x has an absolute maximum. If f of x is continuous, one of these points, either f of a, f of b, well, I guess it wouldn't be a, or something in between, will have to be the highest point on that section. The only way to not have a highest point on the section is if the graph wasn't continuous and maybe went to infinity at an asymptote or something. So I do believe that our last two have to be correct. So both 3 and 4 must be true. Basically, if I can think of a counter example to prove something wrong, that's usually how I go through those, where they say select all apply. This could be like a multiple choice question where the choices are 1 only, 1, 2, and 3, 3 and 4 only, 3 only, 4 only, etc. Concavity. This is a big one that we have not taught in years past in pre-calculus, but it's very important in calculus. And it definitely will show up on our AP Pre-Calc test. So concavity is related to rate of change. The graph of a function is concave up on the intervals in which the rate of change is decreasing. I'm sorry, read that wrong. In which the rate of change is increasing. Concave up, I always think of it like this. Rate of change is increasing. I kind of think of it like concave up is like a smile, and your rate of change is getting more positive, I guess. I don't know. Well, concave up looks like this. Okay, and then concave down. Concave down is when the rate of change is decreasing, like this. Okay. I want to look at well, actually, I want to say something about justification. So to justify concavity, something you'll need to do on the AP test or find the correct multiple choice answer. To justify concavity, you would say exactly this. You would say, why do I know the graph is, or why do I know the rate of change is increasing, or why do I, let's say to justify using concavity. The rate of change is increasing because the graph is concave up. Concave up. Or the rate of change is decreasing because the graph is concave down. Let's look at it on let's look at concavity on like an actual graph. So this is an AP problem that was put out there last spring. It's a practice problem. So the figure shows the graph of a function f. The 0 and extrema for f are labeled, and the point of inflection of the graph f is labeled. Let a, b, c, d, and e represent the x coordinates at those points. Of the following, on which interval is f increasing and the graph concave down? So this shouldn't be too hard to look for. Increasing, concave down is this, increasing is going up, so we're looking for something like that. A to B looks like that. B to C is concave down but decreasing. C to D is concave up but decreasing. And D to E is concave up and increasing. So only A to B. What do we mean by the rate of change is decreasing? Rate of change decreasing. It's important to be able to visualize that. Draw in slopes. Rate of change is slopes. I draw little tangent slopes. Think about this. Super steep. I'm making up a number. M is 12. And then not as steep. M is 8. And then not as steep. M is 2. 1 over 2. And then flat. M is 0. And then M starts getting negative on the next section. Okay? So what we mean by rate of change decreasing is slopes getting, I just want to say lower. No, I want to say shallower. I don't know if shallower is a word, but we're going with it. Why do I say that? Because, well, if you have like negative slopes, think about this one. Concave down, rate of change decreasing. Rate of change decreasing, this is for concave down, right? Are the slopes getting shallower, concave down? No, I don't want to say shallower. See, I keep messing that up. I want to say smaller. But be careful what you mean by that. Smaller slopes for positive numbers get closer to 0. For negative numbers, -10 is smaller than -1. So here, this is like kind of a negative slope, kind of negative, then super steep negative slope. So this is concave down. And then this is concave up because the slope's negative, but then it's starting to get closer to 0 here. So these are getting shallower or smaller, concave up. These slopes are getting bigger, so they're getting closer to 0, right? So concave up, slopes are increasing. Concave down, slopes are decreasing. And just be careful with negative numbers about, yes, negative numbers are decreasing if you're going from -1 to -10. They're increasing if you're going from -10 to -1. I might have confused that a bit in my video. I'm keep mincing my words here, but we will practice this a lot in our AP classroom too. Here's a calculator one. The rate of people entering the subway car on a particular day is modeled by the function r. I wanted to do this one because I want to teach you how to, it's going to be very crucial for your AP exam this year and next year's calculus exam that you can get a graph to show up in your window without any sort of guesswork. So first and foremost, let's type this thing in. Actually, let's read the rest of the question. R of t is measured in people per hour. That's good to know. T is hours since the subway began service. And again, this is the rate of people entering entering a subway car. Based on the model, what value does t give the rate of people entering the subway change from increasing to decreasing? So when does the rate of people entering, when does r of t, this function we're about to graph, change from increasing to decreasing? So don't overthink it. Graph it. 0.03. It says t, but we're going to type in x to the third. Arrow to the right out of that. Minus 0.846 x squared plus 6.587 x plus 1.428. Now, I don't want to guess and check. I don't want to zoom 6. Let's just look at what happens. Zoom 6 does not give me the full picture. This says the domain is 0 to 20. So here's what you do. Press a window. Change the x min and the x max to fit the domain, 0 to 20. I never change the scale unless I'm going from, like, if I want to go from 0 to 200, I might not want the calculator to take the time to make every tick mark 1 unit. I might say count by tens, whatever. 0 to 20. And then don't mess with anything else and press zoom. There's an option 0 right under zoom stat. I'm going to arrow down to get there just to show you. You can press zoom 0. Zoom fit will fit the y values to keep the domain that you set. So it will fit the y values so that everything between inputs 0 and 20, every function value fits in the window you see. Perfect. So there's r of t. Check your window just to see what it did. See how it held the domain in your x scale, and then it changed y min, y max to whatever it wanted to. Well, to whatever actually fit the graph. Okay, so where does the graph change from increasing to decreasing? Increasing to decreasing, and then to increasing again. So the only spot is right here. And to get the exact spot, I want to, well, now I can kind of use guess and check. I'm guessing that it's probably D because the other values look too high. But I want to make sure you know how to find a maximum on your calculator. So second trace, I want to find a maximum. It says left bound. You've got to move your cursor to the left of where you think the maximum is. You're going to help the calculator kind of zero in on where that maximum will be. So I think it's over here. So I'm going to stop my cursor here and press enter. You should see an arrow and like maybe a line. And it says right bound. Move your cursor to the right past the maximum and press enter. And then it says guess, so sure, guess. We'll calculate something that tells us where the maximum is. So Yeah. Now notice the t-value that they have on here, 17.056. They're trying to trick you. That is the y value of the maximum. The question says at what value of t? So we want the x value, which is 5.505. Okay, that's it for today. Our homework will let us practice some of this calculator stuff too.